Hi all. In previous class, we discussed about chemical potential and partial properties of binary solution and derived the equations for partial properties for binary solution. In today's class, we have to discuss about fugacity definition and fugacity coefficient definition. Now coming to fugacity definition. Initially, Gibbs free energy for an ideal gas in terms of fugacity is given by Giz is equals to C of T plus RT ln P. Giz is equals to C of T plus RT ln P. Noted with equation 1. For real fluid, the analogous equation is G is equals to C of T plus RT ln F. Here, replace the term P with fugacity. Here, P is replaced with new property F. F is fugacity. F has the units of pressure, that is bars. The equation 2 is called equation for fugacity. Now subtract equation 1 from 2, that is G minus Giz is equals to C of T plus RT ln P minus C of T plus RT ln F. Subtract equation 1 from 2, that is G minus Giz is equals to C of T plus RT ln F minus C of T minus RT ln P. Therefore, the C of T terms get cancelled and eliminate the term RT. RT into ln F minus ln P. Therefore, RT is equals to, RT ln F by P. ln A minus ln B form. That is ln A by B. Therefore, RT ln F by P. Therefore, G minus Giz is equals to RT ln F. G minus Giz is equals to RT ln phi. Here phi is equals to F by P. Phi is called as fugacity coefficient. The LHS of the equation 3 indicates the absolute values of difference between real and ideal gas Gibbs free energy. Now coming to residual property definition. Residual property is defined as the difference in property between real and ideal gas. Mr is equals to M minus Mic. Mr is the residual property, M is the real property and Ic is the ideal property. M is the general property. We have to replace with M by G, that is Gibbs free energy. Therefore, Gr is equals to G minus Giz. Note this equation with 4. Now substitute equation 4 in 3. That is Gr is equals to RT ln phi. Previously, we derived G minus Giz is equals to RT ln phi. Therefore, Gr is equals to RT ln phi. Taking the term ln phi into right hand side of the equation. Ln phi is equals to Gr by RT. That is denoted with equation 5. For an ideal gas, Gr is equals to Giz minus Gic is equals to G. Initially, we have Gr is equals to Giz minus Gic. Initially we have Gr is equals to G minus Gh. In real gas, we have to substitute with ideal one. That is Gr is equals to Gig minus Gh. That is equals to 0. Previously, we proved that Gr is equals to ln phi. Therefore, phi is equals to 1. That means fugacity coefficient is 1 for an ideal gas. Coming to the calculation of fugacity coefficient. Initially, we consider the fundamental property relation for closed system. At constant temperature, the relation dc is equals to vdp minus sdt term. Initially consider fundamental property relation for closed system. That is G is equals to vdp minus sdt. At constant temperature, the term sdt goes to 0. Therefore, dg is equals to vdp. For an ideal gas, dg/iz is equals to vdp. Therefore, v is equals to RT by P from ideal gas law. That is equals to dg is equals to RT by P into dP. That is denoted with equation 6. For real gas, dg is equals to ZRT by P dP. For ideal gas, Z is equals to 1. For real gas, dc is equals to ZRT by P into dP. Now, subtract equation 6 from 7. Therefore, d of G minus Giz is equals to ZRT by P into dP minus RT by P into dP. dCr is equals to RT by P into Z minus 1 into dP. Therefore, dGr is equals to RT by P into Z minus 1 dP. After differentiating, we will get Gr by RT is equals to integral Z minus 1 into dP by P. Therefore, ln phi is equals to Gr by RT is equals to integral Z minus 1 dP by P. Now coming to the calculation of fugacity coefficient from virial equation. Initially, the virial equation of state Z is equals to 1 plus dP by RT. Integrating both sides of this equation, integral Z minus 1 dP by P is equals to integral BP by RT into dP by P. Here PP get cancelled. Therefore, V by RT is equals to integral dP. Now coming to calculation of fugacity coefficient from virial equation. Initially, we have virial equations of state Z is equals to 1 plus BP by RT. Therefore, Z minus 1 is equals to BP by RT. Integrating this equation on both sides. Integrating the equation on both sides. Integral Z minus 1 dP by P is equals to integral BP by RT into dP by P. Therefore, P gets cancelled. Integral Z minus 1 dP by P is equals to B by RT integral dP. Finally, after integration, ln phi is equals to Bp by RT. At critical conditions, Bpc by RTC is equals to beta naught plus omega beta dash. Here, beta naught, beta dash are the constants. We have to calculate beta naught and beta dash from some correlations. Beta naught is equals to 0.083 minus 0.422 divided by TR power 1.6. B dash is equals to 0.139 minus 0.172 divided by TR power 4.2. Now coming to fugacity coefficient of species I in solution. In solution, species I. For pure species, ln phi is equals to Gr by RT. The above equation can be written for solution. That means total solution. ln phi and cap is equals to G bar R by RT. For solution, fugacity coefficient notated with cap. ln phi I cap is equals to G bar R by RT. For pure species, phi is equals to F by P. Previously, we derived that fugacity coefficient is equals to F by P. For solution or mixer, phi I cap is equals to Fi cap by Yi P. Here Yi is the mole fraction of species R. Therefore, G bar R by RT is equals to dou by dou Ni of Ngr by RT. Initially, differentiate this equation with respect to Ni. Therefore, G bar R by RT is equals to dou by dou Ni of Ngr by RT at constant temperature, pressure and number of moles. Therefore, ln phi is equals to dou n ln phi by dou Ni at constant temperature, pressure and number of moles. Here, G bar R by RT is equals to ln phi I cap. We have to replace with ln phi with B by RT. Therefore, ln phi I cap is equals to P by RT multiplied with dou NB by dou Ni at constant temperature, pressure and number of moles. Therefore, ln phi I cap is equals to P by RT Vi bar. Here Vi bar is the partial property. Previously, we know the definition of partial property. That is Vi bar is equals to dou NB by dou Ni. Partial property is defined as change in property with respect to number of moles. Therefore, ln phi I cap is equals to P by RT Vi bar. For mixture of gas, B is equals to sigma sigma Yi Pij. Here, open the sigma term for binary species. Y1 square B11 plus 2 Y1 Y2 B12 plus Y2 square B22. Here, replace Y1 with 1 minus Y2. Y1 B11 minus Y1 Y2 B11 plus 2 Y1 Y2 B12 plus Y2 B2 minus Y1 Y2 B22. Therefore, B is equals to Y1 Y2 2B12 minus B11 minus B22 plus Y1 B11 plus Y2 B22. Therefore, assume delta 12 is equals to 2B12 minus B11 minus B22. Here replace the term delta 1. B is equals to Y1 B11 plus Y2 B22 plus Y1 Y2 delta 12. Here Y1 is equals to N1 by N. Y2 is equals to N2 by N. Substitute Y1 Y2 in above equation. Then we will get B is equals to N1 by N B11 plus N2 by N plus B22 plus N1 N2 by N square into delta 12. Then NB is equals to N1 B11 plus N2 B22 plus N1 N2 by N into delta 12. Now differentiate the equation with respect to N1. NB is equals to N1 B11 plus N2 B22 plus N1 N2 by N into delta 1. Then differentiate the equation with respect to N1. Dou NB by dou N1 is equals to B11 plus N2 delta 12 multiplied with minus 1 by N plus N1 by N square. Similarly, differentiate with respect to N2. Then we will get the expression for B2 bar. Here B1 bar is equals to B11 plus Y12 square delta 12. B2 bar is equals to B22 plus Y1 square delta 12. Substitute B1 and B2 terms in ln phi 1 cap and ln phi 2 cap. Then we will get ln phi 1 cap is equals to B1 bar P by RT, ln phi 2 cap is equals to B2 bar P by RT. Therefore, ln phi 1 cap is equals to P by RT multiplied with B11 plus Y2 square delta 12. ln phi 2 cap is equals to P by RT into B22 plus Y1 square delta 12. These two formulas are used for calculation of fugacity coefficients in binary solution. Here phi 1 cap and phi 2 cap are the fugacity coefficients. Now coming to fugacity of liquids. Fugacity can be defined by G is equals to C of T plus RT ln F. Apply this equation for liquids. Therefore, GL is equals to C of T plus RT ln FL. Similarly, for gases, Gv is equals to C of T plus RT ln Fv. Note this equation with 3. At equilibrium, Gibbs energy for liquids and vapor are equal. Therefore, GL is equals to Gv. Here, equate the Gibbs energy for liquids and vapor. C of T plus RT ln FL is equals to C of T plus RT ln Fv. C of T terms gets cancelled on both sides. Therefore, ln FL is equals to ln Fv. FL is equals to Fv is equals to Fsat. For a closed system, we have the relation for fundamental property. That is dg is equals to vdp minus sdt. Assume temperature is constant. At constant temperature, dc is equals to vdp. Integrate this equation with respect to gsat to gl, psat to p. Therefore, gsat to gl dz is equals to VL into integral P sat P into dP. Integral G sat to GL dz is equals to VL into integral P sat P to dP. Integral G sat GL dz is equals to VL into integral P sat P dP. After substituting the limits, GL minus G sat is equals to VL into P minus P sat. Now, subtract equation 3 from 2. Therefore, GL minus GV is equals to RT ln FL minus ln FV. Therefore, GL minus GV is equals to RT ln FL by FV. Here, this is in the form of ln A minus ln B. That is written in the form of ln A by B. For saturation, equation 1 becomes to G sat is equals to C of T plus RT ln F sat. Therefore, minus G sat plus GL is equals to RT ln FL minus RT ln F sat. We have to eliminate the term VL and RT. Therefore, VL by RT into P minus P sat is equals to ln FL by F sat. FL by F sat is equals to e power PL by RT into P minus P sat. Taking the term F sat into right hand side of this equation, FL is equals to F sat into e power PL by RT into P minus P sat. Here, F sat is replaced with fugacity coefficient and P sat. This is coming from the definition of fugacity coefficient. Therefore, FL is equals to phi sat into P sat into e power PL by RT into P minus P sat. Therefore, e power PL by RT into P minus P sat is known as Poynting factor. Now coming to fugacity of ideal solution. It serves as a standard to which real solution behavior can be compared. Now coming to fugacity of ideal solution. It serves as a standard to real solution behavior can be compared. This is formalized by introduction of excess properties. For an ideal solution, G bar ID is equals to Gi plus Rt ln Xi. That is noted with equation 1. Here ID denotes solution property. Mu I is equals to C of t plus Rt ln Fi cap. Here Gi bar ID is replaced with mu I and C of t plus Rt ln Fi cap replaced with Xi, where ID denotes solution property. Mu I is equals to C of t plus Rt ln Phi I cap. Equation 2 represents the fugacity of solution. Equation 2 represents the fugacity of species in solution. For ideal solution, fugacity of species in solution is mu id is equals to G bar id is equals to C of t plus Rt ln Fi cap id. Here Gi is equals to C of t plus Rt ln Fi. 4 represents the pure species fugacity equation. Equation 4 represents fugacity equation for pure species. Now substitute equation 4 in 1. Then Gi bar id is equals to C of t plus Rt ln Xi plus Rt ln Fi. Therefore, Gi bar id is equals to C of t plus Rt ln Xi Fi. Here ln A plus ln B form. Then ln A plus ln B is equals to ln AB. That is equals to Gi bar id is equals to C of t plus Rt ln Xi Fi. Compare equations 3 and 5. Fi cap id is equals to Fi x. Then compare the equations 3 and 5. We will get Fi cap id is equals to Fi xi. This equation 6 is called as Lewis-Randall equation. Lewis-Randall rule applies to each species in ideal solution at temperature, pressure and composition. The fugacity of pure species I in ideal solution is directly proportional to its mole fraction multiplied with fugacity of pure species. Here, fugacity of pure species I in an ideal solution is proportional to its mole fraction and proportionality constant is fugacity of pure species I. Now coming to excess properties. Excess property is defined as the difference between actual property of solution to the ideal solution property at the same temperature, pressure and composition. Mathematically, excess properties are denoted with ME is equals to M minus MID. Here M is the general property. Then substitute M with G. Therefore, Ge is equals to G minus Gid. G bar E is equals to Gi bar minus Gid. This is the partial excess Gibbs energy. We know that Gi bar E is equals to C of t plus Rt ln Fi cap minus C of t plus Rt ln Fi cap id. Therefore, Gi bar is equals to Rt ln Fi cap by Fi cap id. This is in the form of ln A minus ln B. Then we write in the form of ln A by B. Therefore, Gi bar is divided by Rt is equals to ln Phi I cap by ln phi I cap by fi cap id is equals to ln gamma I. Here gamma I is the activity coefficient. Gamma I is equals to fi cap by fi cap id. That is equals to fi cap by xi fi. Now coming to the fundamental excess property relation is derives in exactly the same way as the fundamental property residual property relation and leads to the analogous results. d of nge by rt is equals to nve by rt dp minus nhe by rt dt plus sigma gi bar e divided by rt into dni.